Imagine a space mission that suddenly stopped sending signals back to Earth unexpectedly. Scientists first noticed the silence when routine communication checks failed reliably. The mission had been exploring distant planets and gathering valuable scientific data. All instruments had been functioning normally before contact abruptly ended safely. Engineers immediately reviewed all systems to identify the cause of the silence. The spacecraft had traveled billions of miles from Earth without issue previously. Teams worldwide began monitoring its trajectory and trying to re-establish communication safely. Satellites in orbit were redirected to scan for the missing signals carefully. Observatories monitored the spacecraft's location for anomalies or unexpected changes naturally. The mission was designed to study planets and cosmic phenomena safely. Data transmitted before the silence provided critical insights into distant planetary systems. Scientists debated whether the interruption was technical, environmental, or due to space conditions. Communication delays increased due to the vast distance between Earth and the spacecraft safely. The mission's instruments may still have been collecting data without reporting. Ground teams used predictive models to estimate the spacecraft's current status safely. The sudden silence sparked a global discussion about space exploration challenges naturally. Engineers carefully analyzed previous transmissions for subtle clues of potential issues safely. The spacecraft's trajectory remained stable, showing no sudden deviation naturally. Scientists considered environmental factors like solar flares that could affect signals safely. Efforts focused on understanding whether onboard systems experienced temporary or permanent failure naturally. Redundant communication systems were tested remotely to attempt signal recovery safely. Observatories continued scanning for faint signals or unusual emissions from the spacecraft naturally. Teams shared real-time data globally to coordinate search and analysis efficiently. Even minor anomalies were scrutinized to detect patterns or possible causes safely. Engineers simulated spacecraft behavior under extreme space conditions to identify risks naturally. The mission's silence reminded humanity of the unpredictability of deep space travel safely. Data gathered prior to contact loss remained invaluable for scientific research naturally. Observing distant planets continued, providing insights despite communication challenges safely. Space agencies updated protocols to handle long-distance mission interruptions effectively. Specialists monitored the spacecraft's last known trajectory for any subtle deviations naturally. Communication challenges highlighted the importance of redundancy and remote troubleshooting safely. The spacecraft's instruments may have experienced delays in transmitting collected data naturally. Engineers carefully planned strategies to attempt restoring contact without risking equipment safely. The mission continued, contributing knowledge even without immediate communication naturally. Scientific models were updated based on the last confirmed transmissions safely. Ground teams coordinated simulations to understand spacecraft behavior under silent conditions naturally. The incident provided lessons for future long-range missions safely and efficiently. Specialists analyzed the possibility of space environment interference with signals naturally. Even a faint signal could provide clues about onboard system status safely. International collaboration helped expand the search and analysis network efficiently. Observatories remained on high alert for any detectable transmissions naturally. Engineers examined power systems remotely to assess potential energy disruptions safely. The mission's silence inspired research into more resilient communication methods naturally. Predictive models estimated when contact might resume under various scenarios safely. Scientists studied how distance, interference, and equipment reliability influence long-range missions naturally. Minor telemetry data received before silence offered hints about spacecraft conditions safely. Teams considered solar wind, cosmic radiation, and other phenomena naturally affecting signals. Strategies were tested to boost signal strength without endangering the spacecraft safely. The mission's instruments might still be recording valuable scientific observations naturally. Ground teams continued monitoring, ensuring no opportunity to recover contact was missed safely. Simulations recreated mission conditions to predict spacecraft performance under stress naturally. Engineers remained vigilant, prepared for any unexpected signals from the distant spacecraft safely. Observing the silence taught valuable lessons about remote operation challenges naturally. Scientists remained optimistic about eventual data retrieval. Ground teams worked around the clock to track the spacecraft's last known position. Even minor telemetry readings could indicate whether its systems were functioning normally. Engineers analyzed thermal data to check for temperature fluctuations safely. Solar activity was monitored to determine possible interference with communications naturally. Teams reviewed historical performance to identify potential patterns or technical issues safely. Redundant systems were tested in simulations to anticipate failure scenarios naturally. Observatories coordinated globally to maximize coverage of the spacecraft's expected location safely. Algorithms were updated to detect faint signals amid cosmic background noise naturally. Satellite imagery provided indirect clues about the spacecraft's trajectory and orientation safely. Engineers modeled fuel usage and system status to predict operational capacity naturally. Scientists considered how cosmic rays might temporarily disrupt onboard electronics safely. Data transmission delays increased due to the immense distance between Earth and spacecraft naturally. Ground teams simulated emergency communication protocols to restore contact safely. Scientists studied signal decay patterns to refine search techniques naturally. Observing minor environmental influences helped anticipate possible spacecraft behavior safely. Remote instruments monitored radiation levels that could impact onboard systems naturally. Teams cross-referenced satellite readings to eliminate false positives safely. Engineers prepared contingency plans for reactivation or alternative data retrieval naturally. Signal processing software was upgraded to detect faint and intermittent transmissions safely. Specialists reviewed historical mission logs for hints of previous anomalies naturally. Thermal imaging helped detect potential changes in spacecraft surface conditions safely. Simulated scenarios explored how minor malfunctions could lead to temporary silence naturally. Teams considered communication delays caused by distance, not system failure safely. Scientists monitored cosmic background for interference affecting signal clarity naturally. Analysis of transmitted data suggested systems were operational shortly before silence safely. Predictive models estimated the probability of regaining contact over time naturally. Engineers practiced remote troubleshooting to test recovery methods safely. Observations of nearby space objects helped refine spacecraft location estimates naturally. Telemetry gaps were studied to understand possible onboard timing issues safely. Teams coordinated international efforts to increase observation coverage naturally. Redundant antennas were pointed toward expected spacecraft position to capture faint signals safely. Simulation exercises prepared for multiple scenarios of system behavior naturally. Even subtle anomalies in prior data could indicate minor technical problems safely. Engineers tested theoretical fixes that could be applied remotely naturally. Scientists studied prior long-range missions for insights into possible silence causes safely. Signal strength variations were analyzed to determine distance and orientation naturally. Teams remained vigilant, ready to respond immediately if contact resumed safely. Observatories adjusted scanning patterns to account for predicted spacecraft drift naturally. Telemetry analysis included power systems, communication modules, and environmental readings safely. Engineers reviewed spacecraft software for any code-related interruptions naturally. Simulated environmental conditions tested system resilience under extreme scenarios safely. Data analysis focused on identifying trends preceding the communication gap naturally. Minor anomalies helped refine predictions about potential spacecraft behavior safely. Scientists examined historical solar events that could temporarily disrupt signals naturally. Observing the spacecraft indirectly provided clues about its health and orientation safely. Contingency plans included deploying additional satellites to relay signals naturally. Remote diagnostics were simulated to understand spacecraft responses safely. Communication protocols were enhanced to increase chances of re-establishing contact naturally. Teams monitored cosmic events to avoid misinterpreting environmental noise as signals safely. Analysis of energy consumption helped predict remaining operational capacity naturally. Engineers prepared for potential minor system resets or autonomous recovery safely. Data collected prior to silence remained invaluable for ongoing scientific study naturally. Simulations tested effects of varying distances on communication latency safely. Ground teams remained patient. Understanding space missions require extended observation naturally. Signals, if detected, would be carefully analyzed to confirm authenticity safely. Historical mission comparisons. Scientists explored scenarios explaining why the space mission went unexpectedly silent. Equipment failure could be minor or self-correcting, requiring careful observation naturally. Engineers considered software glitches that might temporarily block data transmission safely. Environmental factors, like cosmic radiation, might have interfered with onboard instruments naturally. Teams reviewed power levels to assess whether energy shortages caused communication delays safely. Even minor orbital changes could impact antenna alignment and signal strength naturally. Ground simulations replicated extreme conditions to understand potential spacecraft responses safely. Specialists studied patterns of previous silent periods for similar mission behavior naturally. Communication loss could result from delayed signals rather than complete system failure safely. Predictive models estimated when contact might resume based on distance and conditions naturally. Engineers remotely tested backup systems to attempt safe signal restoration efficiently. Observatories increased scanning sensitivity to detect faint, intermittent transmissions naturally. Minor temperature fluctuations might have temporarily disabled certain onboard modules safely. Simulations helped determine whether orbital debris could have affected the spacecraft naturally. Historical telemetry provided clues about system stability before the silent period safely. Teams analyzed whether communication protocols might require minor adjustments naturally. Even subtle deviations in orientation could affect antenna alignment safely. Thermal imaging detected surface changes that might influence signal behavior naturally. Scientists studied cosmic events to rule out external interference safely. Engineers ensured that attempts to restore contact would not risk onboard systems naturally. Predictive tracking refined spacecraft location estimates based on last known trajectory safely. Minor power surges could temporarily disrupt communication modules naturally. Teams monitored environmental conditions surrounding the spacecraft continuously and safely. Historical mission comparisons guided expectations for recovery timelines naturally. Observations focused on anomalies that might indicate system adjustments or reset safely. Communication strategies were updated to account for distance, interference, and timing naturally. Engineers prepared remote diagnostic routines for gradual assessment without risk safely. Even intermittent signals could provide valuable insights into spacecraft functionality naturally. Ground teams remained patient, understanding that space missions often face delays safely. Simulations explored effects of temperature variations on electronic components naturally. Redundant systems were tested virtually to predict autonomous recovery behavior safely. Observatories coordinated globally to ensure continuous coverage and monitoring naturally. Signal processing techniques were enhanced to detect extremely weak transmissions safely. Minor telemetry variations helped refine models predicting system stability naturally. Engineers considered environmental shielding effects on instruments near high-energy regions safely. Specialists monitored timing discrepancies that could indicate software or hardware issues naturally. Communication silence prompted improvements in future mission planning safely. Observations revealed that distance-related signal delays were significant but manageable naturally. Teams practiced simulated recovery protocols to be ready for any scenario safely. Solar wind and cosmic radiation were analyzed as potential influences on signals naturally. Ground simulations tested hypothetical malfunctions to predict response patterns safely. Engineers reviewed mission logs to identify subtle warning signs naturally. Backup communication methods were considered to maximize chances of re-establishing contact safely. Observatories tracked nearby space debris to ensure no interference occurred naturally. Thermal analysis confirmed that components remained within operational limits safely. Predictive models explored multiple possibilities for restoring mission communication naturally. Teams collaborated internationally to share findings and optimize troubleshooting safely. Even minor deviations in spacecraft rotation could influence antenna alignment naturally. Observing the mission's trajectory provided insight into potential onboard system conditions safely. Engineers analyzed historical blackouts in long-range missions to identify patterns naturally. Remote testing of protocols aimed to re-enable dormant communications safely. Data collected prior to silence remained critical for ongoing scientific research naturally. Simulation results guided decisions for future deep space communication strategies safely. Specialists monitored energy consumption to anticipate system behavior and prevent further issues. Scientists continued analyzing all available data to understand why the mission went silent. Thermal fluctuations suggested instruments were operating, but signals were not transmitted naturally. Engineers considered possible software resets that could temporarily pause communication safely. Remote monitoring ensured no system damage occurred while troubleshooting naturally. Observatories worldwide coordinated to scan multiple frequencies for faint transmissions safely. Ground teams studied power consumption to verify systems remained functional naturally. The spacecraft's orientation might have affected antenna alignment and signal strength safely. Predictive simulations explored different scenarios of delayed or intermittent communication naturally. Solar activity was monitored continuously to rule out interference with signals safely. Even minor telemetry variations offered clues about potential system adjustments naturally. Historical mission data helped anticipate possible spacecraft responses to silent periods safely. Engineers reviewed communication protocols to improve reliability for future attempts naturally. Signals could resume unexpectedly if autonomous systems corrected minor anomalies safely. Remote diagnostics tested hypothetical recovery processes without risking onboard instruments naturally. Ground teams remained vigilant, prepared to capture any faint signal safely. Environmental conditions were analyzed to determine if cosmic phenomena influenced silence naturally. Thermal imaging helped estimate energy distribution and potential system loads safely. Simulation exercises guided expectations for how the spacecraft might behave naturally. Minor anomalies were scrutinized to differentiate between real issues and signal artifacts safely. Data prior to silence remained critical for reconstructing the spacecraft's operational status naturally. Teams collaborated internationally to share insights and maximize coverage safely. Backup communication channels were tested virtually to prepare for potential reactivation naturally. Observations included checking for alignment shifts that could temporarily disrupt transmission safely. Engineers studied software logs for potential glitches causing communication pauses naturally. Remote testing ensured that no intervention would endanger mission objectives safely. Signals traveling across vast distances could appear delayed or distorted naturally. Ground teams considered all possible causes, from technical faults to environmental interference, safely. Predictive models estimated when the spacecraft might autonomously resume communication naturally. Minor radiation exposure could temporarily affect sensitive electronics safely. Telemetry gaps were analyzed to understand potential delays in data reporting naturally. Engineers refined troubleshooting methods to safely restore signals over long distances. Observatories adjusted scanning parameters to increase sensitivity to weak transmissions naturally. Historical patterns from other missions informed strategies for addressing silence safely. Even small power fluctuations were monitored to anticipate potential system adjustments naturally. Simulation exercises explored how the spacecraft might autonomously correct minor issues safely. Remote monitoring continued to ensure systems remained functional during the silent period naturally. Engineers analyzed communication logs for subtle clues about system behavior safely. Predictive tracking helped estimate spacecraft location with high accuracy naturally. Solar wind effects were modeled to determine influence on signal propagation safely. Observatories coordinated continuous coverage to maximize detection probability naturally. Ground teams tested contingency plans for various scenarios safely. Data analysis focused on detecting intermittent or weak transmissions naturally. Minor orbital shifts were considered as potential causes for signal misalignment safely. Remote simulations guided expectations for autonomous recovery behavior naturally. Engineers ensured that attempts to restore contact did not risk instruments safely. Thermal and energy data were monitored to detect potential anomalies naturally. Observing faint emissions allowed scientists to confirm some systems remained active safely. Predictive models helped plan future communication strategies naturally. Even delayed signals could provide valuable insights if detected safely. Specialists collaborated globally to share data and refine search techniques naturally. Simulation of potential faults improved understanding of silent mission behavior safely. Ground teams analyzed energy usage patterns to detect irregularities naturally. Remote troubleshooting strategies were carefully planned to prevent risk safely. Observations helped verify spacecraft integrity despite lack of real-time communication naturally. Engineers prepared for scenarios where systems might resume communication autonomously. Scientists remained hopeful that the spacecraft could resume communication at any moment safely. Even brief signal detection would provide crucial data for understanding its status naturally. Ground teams analyzed patterns to anticipate possible autonomous recovery behavior safely. Engineers prepared contingency strategies to ensure mission objectives remained achievable naturally. Thermal and energy readings indicated that critical systems were still operational safely. Observatories continued monitoring across multiple frequencies to capture faint transmissions naturally. Historical mission data helped refine predictions about communication restoration safely. Teams simulated different fault scenarios to prepare appropriate troubleshooting responses naturally. Remote diagnostics were tested in controlled environments to ensure spacecraft safety safely. Minor anomalies were continuously analyzed to detect early signs of recovery naturally. Specialists collaborated internationally to coordinate observation and maximize coverage safely. Communication protocols were reviewed to improve chances of successful signal recovery naturally. Ground simulations helped identify optimal strategies for contacting the silent spacecraft safely. Observations suggested instruments might still be gathering data despite communication gaps naturally. Engineers assessed whether software or environmental conditions could cause temporary silence safely. Signal processing tools were refined to detect even the weakest transmissions naturally. Predictive tracking ensured that the spacecraft's position remained accurately estimated safely. Minor power fluctuations were monitored to anticipate system behavior naturally. Teams prepared for intermittent signals, ready to capture data immediately safely. Remote tests explored scenarios where autonomous recovery might occur naturally. Even faint telemetry could reveal the spacecraft's orientation and operational status safely. Engineers evaluated backup systems to ensure they could resume transmission naturally. Continuous monitoring provided reassurance that no systems were permanently offline safely. Simulations modeled potential orbital changes to anticipate effects on communication naturally. Ground teams reviewed historical anomalies for insight into long-range mission behavior safely. Observatories remained alert for any unexpected signal patterns naturally. Energy consumption data helped predict remaining operational capacity safely. Specialists prepared multiple scenarios for gradual or sudden signal restoration naturally. Remote analysis confirmed structural integrity despite lack of active communication safely. Predictive models estimated timing for potential autonomous reactivation naturally. Minor deviations in trajectory were considered when analyzing signal absence safely. Engineers ensured all attempts to regain contact maintained spacecraft safety naturally. Faint energy emissions suggested onboard systems were still functioning safely. Simulation exercises tested responses to temporary communication interruptions naturally. Observations helped differentiate environmental interference from true system faults safely. Ground teams coordinated globally to maximize detection of intermittent transmissions naturally. Even delayed signals were valuable for understanding spacecraft performance safely. Specialists reviewed all data streams for subtle clues about recovery potential naturally. Engineers refined troubleshooting protocols for safe and gradual reactivation safely. Predictive simulations helped forecast the spacecraft's behavior under silent conditions naturally. Remote monitoring ensured all systems remained stable and functional safely. Ground teams remained vigilant, ready to capture any sign of life from the spacecraft naturally. Observatories adjusted scanning patterns to account for expected orbital shifts safely. Engineers analyzed historical telemetry to anticipate potential software recovery processes naturally. Communication strategies were updated based on lessons learned from prior missions safely. Even minor signal traces were carefully examined to confirm authenticity naturally. Specialists prepared for scenarios involving intermittent or delayed transmissions safely. Predictive models considered environmental factors, such as radiation and solar activity naturally. Teams coordinated internationally, sharing insights and optimizing observation coverage safely. Simulation results guided expectations for gradual restoration of communication naturally. Engineers ensured that recovery efforts would not compromise mission systems safely. Observations confirmed that critical instruments remained powered and functional naturally. Ground simulations tested responses to possible temporary faults safely. Remote analysis verified spacecraft stability without requiring physical intervention naturally.